Hey everyone, welcome to another video. Today we're looking at gradient and direct proportion. Now, this is a topic that ties together linear relationships with some of the other things we've been talking about in other courses. And this is the idea of rates and how one thing changes in relation to another thing. Now, the idea of something being directly proportional, some direct proportion, means that one thing changes with another at a constant rate. Now, where does this look familiar? Well, hopefully you may think back to any time we've drawn some linear relationship. When I, for example, have, something like this. What linear relationships told us was that there was always a constant gradient for these particular things. So as x changed by 1, y would always change by the same thing. So for example, x changes by 1, y changes by 2. X changes by 1, y changes by 2. This is an example of something being directly proportional. The change in y is always, for every change in x, is always going to be constant. And this is where the idea of something being linear comes in. We have a constant gradient for our lines. So no matter which direction I go in, my change in y will always be directly proportional to my change in x. Now, let's look at this through the lens of a real world example. Now, I'm going to rub this off and let's start with something that I hope is going to be at least more relevant to us than x's and y's, right? Now, I really like cookies, for example. So every now and again, if I'm home, I'll dig into a box of cookies. Now, and that's me over here, right? Now, every cookie I take has a certain amount of calories to it, right? So it has a certain amount of energy it's going to give me. So I'm going to write that here. Each cookie has a certain amount of calories. And the calories for each cookie is going to be the same if we're assuming that these are made identical shapes and sizes with the same ingredients, so on and so forth. But each cookie has the same amount of calories. So let's say on the back of my cookie box, I have that there are 200, let's do a smaller number. Let's say 100 calories per cookie. Okay, so I'm going to get 100 calories of energy per each cookie. So that means if I have one cookie, let's draw this in a cookie color, we'll go brown. If I have one cookie, that is 100 calories. Another cookie is going to be 100 calories. So how much were how many calories, for example, do I have altogether? Well, if I have 100 calories for one cookie, I can say that I have 200 calories for two cookies. And this is going to keep going up. If I add a third cookie here, that's another 100 calories. So I have, well, cool, instead of 200 calories, I've added another 100 calories to this. So I have 300 calories for 3 cookies. Can you see that my amount of calories that I'm adding is proportional to the amount of cookies I have? it's increasing at a constant rate. I had started off with one cookie. That was 100 calories. Each cookie that I added, I increased by the same amount of calories. See, I went from 100 to 200 to 300 calories. So for each cookie I added, I got another 100 calories. And what linear relationships allows us to do is graph these things that are directly proportional, that change at the same rate. So if I were to, for example, graph my cookie intake, well, my cookie consumption, and then my calorie intake, I'm going to get what we call a linear relationship, which is what we've been dealing with this whole time. Now, if I graph this, for example, and I had, oops, and I had, instead of, so I don't do calories and cookies, those both start with C. Let me write E for energy, and I'm going to write C for cookies. So if I graphed my cookie intake versus the subsequent calorie intake, I go 1, 2, 3 cookies. Let's do 4 as well. And I want to graph this along with my energy intake. So 100 calories, 200 calories, 300 calories, and 400 calories. Well, if I have one cookie, I take in 100 calories. So that acts as a point on my graph. So when I have when I have one cookie, I get 100 calories. When I have 2 cookies, for example, I get 200 calories in my system. When I have 3 cookies, I have 300 calories of energy in my system. And so on and so forth. Now, if I drew a line through this, well, I would get, it's not going to be perfect, but I get what we call a linear relationship. And it's important to note as well that when I've had 0 cookies, how many calories have I taken in? Well, I've taken in 0. So we're starting at the point 0, 0. So what we've done here is we've just taken everything we know about linear relationships and plotting points on a graph and drawing the graph. We are applying this now to rates. We're applying this to a rate of 100 calories per cookie. So what we end up getting is a linear relationship. So we can say that the calories consumed are directly proportionate to the cookies eaten. So that means as I constantly increase my number of cookies, so I go from 1 to 2 to 3 to 4, I am constantly increasing the same calories. 1, 2, 100, 200, 300, 400. Do you notice I'm taking these same kinds of steps that I did in linear relationships? So I can write this idea of consuming cookies as a linear relationship, as a relationship between 2 variables. Now, instead of X and Y now, I have E, the energy I get in calories, for C, for the amount of cookies I get. Now, let's think, how could we write this out? Well, my Y-axis is going to be E here, and that's going to equal something in front of my amount of cookies plus something else. Now, if I look at this with my linear relationships hat on, I can't draw a plus to save my life, sorry. Okay. I want to express this as a linear relationship. Well, this thing here, that's my y-intercept. Now, what's my y-intercept going to be here? Well, I start off at 0 calories, right? Because I haven't eaten any cookies. So my y-intercept here is actually 0. So I can write that in, let's do it in a different color, into here. I have I have an intercept, but it's 0 because I haven't consumed any cookies yet, so I have 0 calories in my system. Now, by how much is my energy increasing for each cookie consumed? Well, what that is my gradient. My gradient tells me how much my y variable changes, in this case it's e, for each change in my x variable. Well, let's look that as my cookies go up, my my energy, my calories are going up by 100. So that is going to be my coefficient in front of C, or the x if we wrote this as y equals mx plus b. This is the idea of constant direct proportion. Now, I could have also found this with rise over run. I could have gone, okay, well, m equals, it goes up by 100 for each change in one, and that once again gives me 100. I could have done this in both ways, but the gradient just tells us how one thing changes with another. And here, for each cookie I consume, my gradient goes up. Well, my energy I get goes up by 100 each time. So the linear relationship I end up with here is E equals 100C. So I can now substitute anything I want for E or for C. So I can say, all right, well, if I wanted to answer some questions, let's say one, how many calories do I have for, let's say, 8 cookies? Well, I have my energy equals to 100 times, and here I have a number of cookies, which I'm going to substitute up here in my linear relationship. So I'm going to be multiplying 100 by 8, which gives me 800 calories. This is how we can work through gradient and direct proportion questions. Now I have one more question here that we'll work on together, and I'll just go through drawing the graph, and then we'll establish a rule and a gradient, and then you guys can have a go at finding part D on your own at home. So water is poured into an empty tank at a constant rate. So this is going to be some type of linear relationship. So it's a constant rate. It takes 3 hours to fill the tank with 6,000 liters. Now for part A, what is the rate at which water is poured into the tank? Now if we put on our rates caps back on from things we're doing in that topic, I have 6,000 liters in 3 hours. Now, rates always get written as some measurement or some quantity, some unit per another unit, but per one other unit. So here we have liters in 3 hours. We want to write this as a proper rate. We want to write this as liter per 1 hour. So we want to get these 3 hours to 1 hour. Now, how can we do that? I'll go through this a bit quicker because I've covered all this in my rates series. I have to divide both by 3. If I have 6,000 in 3 hours, that's going to give me, and I divide this by 3, that's going to give me an amount of liters per 1 hour, which is what we need to write a rate. So this is 6,000 liters per hour, per 1 hour. Sorry. That's when we divide 6,000 by 3, that gives me 2,000 liters per 1 hour. Now, the second bit requires us to graph volume, a graph of volume in liters versus time in hours. So the time from 0 to 3 hours. So for part B, I'm going to draw a graph of volume versus time. And here I go from 0 to 1, 2, 3 hours, and my volume is up here. So let's write that as, let's go 1,000, 2,000, 3,000, 4,000, 5,000, and we'll put 6,000 up here. I want to draw a graph, and I'm told that the empty tank is getting filled by water at a constant rate. So for each hour, I'm going up by 2,000 liters. So I start at 0. I have an empty tank. I start here. And at 1 hour, my thing gets filled to 2,000 liters. So at 1 hour, I fill 2,000 liters. And for each increasing hour, I'm going up by 2,000 liters. So when another hour passes, I go up another 2,000 liters. So I go from 2,000 to 4,000. This is my next point. And as a third hour passes, I go up by another 2,000 liters. And voila, I have what looks like a pretty linear relationship if I were to connect these dots. Now, this isn't going to look great because my drawing isn't to scale, but I can see that my volume is increasing in proportion to the time passing. As I go up by 1 in my time, I go up by 2,000 in my volume. As another hour passes, I go up another 2,000 liters. As 1 hour passes, I go up by another 2,000 liters. This is my graph, and I did this using the rate I came up with. If it goes up 2,000 liters each hour, I can pretty easily show this by just tracking, okay, as each hour passes, I'm going up by 2,000 liters, which we can hopefully see here. Now, for part C and D, let's do that here. Just for part C, I want to find both the gradient of our graph and a rule for the volume, for relating volume to time. Well, I just showed here in my graph that for each change in t, each hour passing, I'm going up by 2,000 in my volume direction. As I run along 1 in the time, I rise up 2,000 in my volume. And I can write my gradient as my rise over my run. And my rise is 2,000 liters, and my run is 1 hour. So I can write my gradient as 2,000 here. And now I just need to write a rule for V. So all of my rules, all of my linear relationships, they start with that general formula of a line, y equals mx plus b or plus c. But instead of writing y and x, I'm going to write v and t. So I can write my volume equals, Well, my gradient is 2000. So 2000 t plus, now let's think of what goes in this box here. This thing here is my y-intercept. Now, even though it looks like it's a bit higher, that's just the scale of my graph. It's just not very well drawn out. But if I think about if I've filled up 2000 in 1 hour, what have I started with? At the time zero, at 0 hours, well, I haven't even started filling the tank. So my intercept is actually going to be 0 here. And we can kind of see this. We're going down. If we look from right to left, for example, I start at 6,000, go down 2,000 to 4,000, go down another 2,000 to 2,000, and go down another 2,000 to 0. So my number here is 0, which we can just rub out then. So I'm left with an expression, a rule for V, which is V equals 2000 T. And I can use this now to make predictions like in question D. So you guys can try this at home. Use this rule to find the volume after 1.5 hours or the time to fill 5,000 liters. And that just involves us substituting these numbers into the rule. And once we have the rule, that's the hardest part. Everything else becomes a lot easier. Thank you for watching, guys. I'll see you in the next video.